Assalamualaikum friends. Today we're going to study the concepts of hybridization in chemistry. To understand the concepts of hybridization, firstly we need to know what is hybridization and why the concept of hybridization was needed. Hybridization is basically known as atomic orbital hybridization, which basically means it is related to atomic orbitals. Atomic orbital hybridization. Before the atomic orbital hybridization theory, there was a theory named as Valence bond theory. According to VBT, the partially filled atomic orbitals overlap to form bonds, but the individual characters of atomic orbitals are retained. Greater the overlap, the stronger will be the bond. This was the Valence bond theory. But due to the limitations of valence bond theory, a new theory was required, and now we will see what were the limitations of valence bond theory. To understand those limitations, we need to focus on the structure of CH4. In the structure of CH4, there is one atom of carbon and 4 atoms of hydrogen. Considering the ground state electronic configuration of carbon atom, we got to know that the ground state electronic configuration of carbon atom was 1s2, 2s2, and 2p2. That means that 1s2 has 2 electrons, 2s2 had 2 electrons, and 2p2 had 2 electrons, and one is in 2px and the other is in 2py. Now, in the excited state of carbon atom, an electron will jump into the p orbital. This is how it is going to happen. An electron from the 2s2 will jump into the 2pz. This is known as the excited state of carbon atom. So according to valence bond theory, these orbitals overlap to form new atomic orbitals, but according to this theory, the individual characters of atomic orbitals are retained. So we got to know that when the bond between hydrogen and carbon is formed, there is one orbital named as S, and the other 3 are named as P, which are respectively 2px, 2py, and 2pz. When the hydrogen forms a bond, as we know hydrogen has only 1 electron, that means it has only s orbital. So when the s orbital will form a bond with the carbon atom orbitals, there will be an s-s overlap, and the others will be the sp overlaps, like s-s overlap for one atom of hydrogen and the atomic orbital of carbon, and the other overlaps will be sp overlaps. Here, by the experimental analysis, we got to know that all the 4 bonds in CH4 are equal in length, are equivalent in all respects, like bond length or bond energies. But when we see this according to the valence bond theory, we got to know that there is one different bond and 3 similar bonds, like SS is different overlap and SP, SP, SP are same overlap. Here we needed a new theory to explain this bonding situation. So the limitations of valence bond theory are that it failed to explain the paramagnetic behavior of oxygen, and it did not explain equivalent tetravalency of carbon in methane. So we needed a new theory, which was a hybridization theory, which means mixing of orbitals having different shapes and different energies to form a hybrid orbital which have same energy. Like we are mixing 2 different shaped and different energy orbitals to form similar orbitals, like similar orbitals which have same shape and energy. These orbitals are named as atomic hybrid orbitals. This is the basic of atomic orbital hybridization theory. Practically, this theory means that if 1s orbital is mixed with 3p orbitals, then the hybridized orbitals will be sp3 because there is 1s and 3p, sp3, sp3, and sp3, like 4 sp3 orbitals form after the mixing of s and 3p orbitals. So if we take a look at this hybridization theory and the VBT, we got to know that hybridization theory gives a satisfactory explanation about the bond lengths of CH4, but it changes the geometry of the CH4 molecule. These small circles are for s orbitals, and the lobe-shaped orbitals are the sp3 hybridized orbitals. Here in CH4, the sp3 orbitals after hybridization will make an overlap with the s orbitals of the hydrogen, and here a bond will be formed. This is the chemical bonding explained on the basis of hybridization. This was a basic overview for the hybridization theory. And as we see, the same bond lengths are there, same energies are there in the sp3s overlap, and geometry is changed. Now, heading towards the important points of hybridization theory, which are, according to me, the most important ones that you need to understand before learning or getting towards the structures of different molecules. So the very first point is that intermixing of same or nearly same energy orbitals to form new hybrid orbitals having the same energy, which was also in the definition. It means that the parent orbitals are converted into the new individual orbitals when the 2 parents or 3 parents or 4 orbitals or 7 orbital parents are mixed. That means parent orbitals mix and form hybrid kids, which are the new hybrid orbitals, which will next take part in the bond formation or the chemical bond. The next point that is very important is that number of hybrid orbitals is equal to the number of parent orbitals which are intermixing. Like the number of hybrid orbitals which are formed after the mixing of the parent orbitals is always same to the number of the parents which are mixing. Now the question arises that which type of orbitals can take part in the hybridization. In the hybridization process, half-filled orbitals, fully filled orbitals, and empty orbitals, which are the vacant orbitals, can take part in the hybridization. There is no limitation to the fully filled orbitals, that fully filled orbitals cannot take part in the hybridization, or the half-filled orbitals cannot take part in the hybridization, or empty orbitals cannot take part in the hybridization process. Any of these 3 orbitals can take part in the hybridization process. This is a very important point. The fourth point is that there is no link of the pi bond in the hybridization process. Only sigma bond, which is a single bond that is related to the hybridization process. The fifth point is that the orbitals are always named after the parent orbitals. Like if one s and one p orbital is combining or intermixing, the resulting orbitals will be 2, but the name will be sp orbital. This is the naming point of the orbitals. The hybrid orbitals are always named after the parent orbitals. If there is one s orbital or 2 p orbitals, then the name will be sp2. If there is only one s and 3 p orbital, the name will be sp3, because there are 3 p orbitals, because they're always named after the parent orbitals, which are mixing together to make an hybrid orbital. If there is a 1s, 3p, and 1d, then the orbitals are named as sp3d orbitals. Here I have demonstrated all of the 6 atomic orbital hybridization types to explain you that the names are always after the parent orbitals. Here we see that the sp3 and d orbital, there is 1s, 3p, and 1d, which means 5 hybridized orbitals will be formed. And in the next one, it is that 6 orbitals will form. And in 1s, 3p, 3d, there will be 7 hybridized orbitals. It is clearly seen in the demonstration. The next point is that the hybrid orbitals change their geometry. Like if hybridization is occurring, the geometry of the molecule will change, and the hybrid orbitals will orientate such that the repulsion is at the minimum. That is why the hybridization changes the geometry of the molecules. Hybridization causes the molecule to be more stable and changes its geometry. The last and the most important point in the important points of the hybridization theory are that the shape of the hybrid orbitals. How will you recognize the shape of the hybrid orbitals in your book, or how will you draw the hybrid orbitals? There is a difference in the normal orbitals and the hybrid orbitals and how you demonstrate them. As S orbital has its own shape, P orbital has its own shape, and D orbital has its own shape, the hybrid orbitals also have their own shape. When the orbitals are hybridized, there is a bigger lobe and a smaller lobe. Most of the time, the smaller lobe is ignored in the structure drawing, like in the structure of the CH4. We ignore the small lobe, but the bigger lobe is always not ignored, and the bigger lobe is drawn a bit bigger than the normal lobes of like p orbital or d orbital.